Hello, everyone. In this lecture, we're going to talk about the conservation of forces, the potential energy, and conservation of energy. So, for doing that, we're going to talk about the using of the concept of the conservation of forces and determine the potential energy of such kind of forces, and then apply the principle of conservation of energy for the dynamic problem. First, let's look at some examples. As you can see, there is a spring here that holds some weight. The weight of these sacks of this spring is resting on that platform, which causes some kind of the potential energy to be stored in the supporting the spring on that structure. Uh, if you start removing these loads, the platform gonna rise slightly, since some of these potential energy in the spring gonna transform to increase the gravitational potential energy of the load. And there is some kind of conversion of the energy happens here. Let's say if you are having 100 pound and then the spring constant equal to 500 pound per feet, what gonna be that kind of the energy that you are having in this situation? Another example, a roller coaster again. Yeah, suppose that the car is releasing from the rest on the top of the hill at point A, and then it moves down. The potential energy gonna change and convert to some kind of the kinetic energy. The question is that what is the velocity of the car when it reaches to the point B and C? Because we need those values to design that kind of the structures, and then how we can find the minimum height of the hill A such that we have enough velocity on those points, right? So those are the questions. Now we want to talk about the conservative forces and see what does that mean. So the definition of the conservative force is that that's the kind of the force that work that is being done is independent of the path. So we know that the work is when the force is doing some displacement or doing some work over a distance, which is they are in the same direction line. Now we can have a different path between point A and B. It could be a curve, it could be uh, like a graph or something like that. But if you are having a different type of the path, does it really influence your work? It might be, but if it is independent of the past, then we are saying that we are talking about some kind of the conservative force. And the integration of the force over the distance, which gonna give you the work, gonna be equal to 0. So we are saying that the work is conserved. And because of that, we can say that the work that is done by the conservative force depends only on the position of the particle, not really the path that it moves forward. If we want to do another type of the definitions for the conservative force, we can use some parameters or some new concept, which we call it potential function. And it coming from actually the differential calculus, if you remember that. So we just, for now, gonna stay with the same definitions. Now we are talking about the conservative potential energy of the particle. We can write it down in terms of the potential functions, and we can introduce that the total potential function for a conservative force is composed of the two major sections. One of them is coming from the gravity and another one coming from the spring characteristics of the system. Both of them can have and can influence the potential energy in a particle. So the potential energy is the measurement amount of the work of a conservative force that will do on a body when it has changing the position. Then, as we just said, we can divide it to the two major section, the potential energy from the gravity and the potential energy from the spring. Now let's talk about which potentials, what do they really mean? The potentials from the gravity and the potential from the spring. So first, the potential from the gravity. If you look at these schematics here, you can see the potential function for the gravity force. We can define it as a amount of the weight, because it's also under the influence of the gravity multiplied by the distance that it moves upward on the line of the gravitational field. So it really depends where is your datum or the reference line is. If you go upward, it means that you are having a positive potential energy. And if you go downward, it means that you are having a negative potential energy. Next is that let's talk about the potential energy coming from the spring, or in another word, the elastic potential energy. So suppose that you are having a spring in a rest condition. If you start stretching that kind of the spring, it can have some kind of the energy stored in the spring and tries to move your particle back. So we can define it as the because we already now know that the force in the spring equals to Ks, the potential energy, if you multiply it by distance and do that kind of the integration, we're gonna end up with the potential energy equals to half or 1/2 multiplied by the spring constant, and then the displacement square. That's the difference that we had the similar things before, so we need to really be careful about it. Now, how we can use it in the conservation of the energy. So for the conservation of energy, we are saying that when the particle acts upon a system of conservative force, the work of the force is conserved in such that the sum of the kinetic energy and sum of the potential energy gonna remain constant in the first situation, number one, and in the second situation, number two. And you already remembered that the kinetic energy equals to 1/2 m, which is mass velocity squared. Let's practice the concept. The first question says that the potential energy of a spring, how you can gonna find it? And the answer is that it's always positive, because you are having 1/2 positive value, k positive value, and then the s square, which is always positive. The second question says that when the potential energy of a conservative system increases, the kinetic energy is always decreasing, because we know that you are talking about some kind of the constant variables. All right, an example here. Look at these schematics. We are having a 4 kilogram collar here and has a velocity of 2 meters per second at point A at this location. The spring constant is 400 Newton meter. The unstretched length of the spring is 0.2 meters. We want to find what's gonna be the velocity of this collar at point B when it moves down the line like this. What's gonna be the velocity on this situation? We can apply the conservation of the energy equation between point A and B, and we can notice that there is some kind of the gravitational force, there is some kind of the spring potential, and then there is a velocity involved. It means that the kinetic energy involved, and we can do the calculations. For doing that, let's consider two positions, position number A and position number B, and find out what kind of the energies we have at each location. So the potential energy at point B is gonna have two parts if you are considering the datum line on the top at A, one of them coming from the elastic or the spring, because the spring gonna have some stretches here. And then the another part coming from the gravity, because you are having a change in the elevation. So the first part from the elastic equals to 1/2 a spring constant, the change in the spring displacement square. And the potential energy, your object is actually coming down. So you're having a negative value of the potential energy. And then your kinetic energy at point B gonna be equal 1/2 m velocity squared. Do you know what is the velocity? Not at this point. However, you already write down all of the potential and the kinetic energies. Now to look at the point A as well, right? What do we have at point A? We do know what is the velocity, so we can write what is the TA or the kinetic energy. And then the potential energy at point A is just coming from the spring, right? Because it is right on the datum line and it doesn't have any gravitational energy. And the length of the spring on that point is 0.1. It means that it was compressed a little bit. So you are having a part from the potential, a part from the kinetic. Now, addition of the all energies at point A must be equal to the point B. Let's write it down. If you write it down, it says that the TA plus VA, where all the energies at the A, gonna be all the energies at the B. Let's plug in everything that you have here. You can see the only unknown variable gonna be the velocity at point B, and from this you can find that the velocity in point B gonna be equal to 1.96 meters per second. That's how, from the conservation of the energy, we can find the different dynamic parameters for the system. So this was the topic on the conservation of the forces and the conservation of the energies, and how we can identify what kind of parameters we can get if we know two different energy situations and two different points.